Today we're covering a section of cardiovascular physiology, and in particular, the electrocardiograms, or labeled as ECG or EKG, both representing electrocardiograms. So to start, someone might ask, what is an EKG? Or what it measures or records, to be more exact. And an EKG is a recording of the sum of multiple action potentials from the surface of the body. Now to quickly recap what an action potential is. An action potential is an all or none change in the electrical potential across the cell membrane. Now this could also be called a membrane potential, labeled with Vm. Now going more in tune with our cardiovascular approach, ventricular action potentials are recorded from a single cell intracellularly. This kind of marks the big difference between an EKG and an action potential. But we're going to look at a general action potential graph. Now looking at this general action potential, this is not a ventricular action potential, by the way, we can start labeling a few things. First, we can label the threshold value, which would be around, for a general neuron, is negative 55 millivolts. And we can see that's resting voltage is around 70. So this dotted line represents the resting. Now we actually look at the line that creates. So what we can see here is once it reaches the threshold, that's when the action potential fires. So there has to be a stimulus here, a stimulus that causes the voltage in the cell membrane to reach negative 55 millivolts or higher, and then the action potential fires. Now once it fires, there's a few things that we can see here. First is this upward event. This is called depolarization. And right after the peak, we can see this downward event. This is called repolarization. And finally, we can see it going below the resting potential, which this action or event of going below it is called hyperpolarization. Now, what these mean are, we can first look at what depolarization is. It's making the voltage in the membrane become more positive, while repolarization is the voltage in the membrane becoming more negative, or more closer back to resting potential, as we can see from looking at the y-axis. Now with hyperpolarization, this is when it overcorrects, when the cell overcorrects and it becomes a lot more negative. That's why it's called a hyperpolarization. It's going below the resting and having a more negative voltage. And finally, it does come back to rest here and restabilizes, waiting for the next action potential. Now let's look at an example of an EKG waveform. This is what a single byte of a EKG waveform would look like. And to start, we can start defining some points to this graph. So first, I'm going to label all the points in pink. So here, this small little bump at the start is what we call the P wave. And after the P wave, we see this sharp dip downwards. This sharp dip is part of this big complex here, and the start of the complex is Q, or you could call it the Q wave. The peak of this complex is the R wave, and back down here with the second sharp dip is the S. Together, this is the QRS complex. Now we go on to this second bump that is larger than the P wave. This is what we would call the T wave. And this is all the labeled waves of a EKG. Now, before analyzing any further, there's one thing to mention again, which is EKG waveforms are not action potentials. And in this case, we're going to look now at a ventricular action potential, not just a general one. Now looking at these two, the first thing we can see is that the EKG is much smaller than the ventricular action potential, and this is due to the EKG being recorded from the surface of the body, with this action potential being recorded intracellularly on one cell. And one thing that could make some people confused is that these upward and downward deflections on the EKG don't represent depolarization or repolarization moments like an action potential does, with depolarization going up. That does not correlate to the EKG waveform. Now this can be, again, very confusing to some people, but once you understand why it's like this, it becomes more understandable. First, we can explain what these upward and downward deflections on the EKG represent. So first, we'll observe how we're even recording an EKG. We record EKGs with a heart monitor of sorts that is made up of multiple electrodes, but to simplify it, we're only going to use two, a negative electrode and a positive electrode. Now our deflections in here of going up and down are dependent on whether the depolarizing waves are approaching the positive node or they're going away from it. Now when the depolarizing waves go away from the positive electrode, there's going to be a deflection downward. So we can see that in multiple areas here on all the waves basically. So the depolarizing waves going away from the positive electrode is making a downward deflection, while depolarizing waves going towards the positive electrode makes these upward deflections. Not having anything to do with a hyperpolarization, depolarization, or repolarization. This is recording depolarizing waves. Now I said that we were recording whether the depolarizing waves are going away or towards the positive electrode. Now what is the negative electrode for? The negative electrode is used for reference. So our main electrode here that we're recording from is our positive electrode, with negative, again, just being a reference electrode. Now to kind of complete the EKG definition, we are recording the sum of depolarizing waves going towards or away from the positive electrode from the surface of the body. Now with that aside, let's look more into how our EKG wave is split up. First, we'll look at two intervals. The first interval we'll look at is the PR interval. Now the PR interval starts at the beginning of our P wave and ends right before our Q wave starts. This is what we call our PR interval. And now our second interval is from the start of our Q wave here, where the PR interval ends, all the way to the end of our T wave. This is the QT interval. Now with those two intervals out of the way, we can move on to our segments, which we have two of. Now our segments are split up by our QRS complex. So we'll do the complex in orange, which our QRS complex starts at the beginning of our Q wave and again at the end of our S wave. And this entire block here is our QRS complex. Now we can move on to our segments, which I'll put in yellow. So the first segment we'll look at is our PR segment, which should not be confused with PR interval. Our PR segment starts at the end of our P wave and ends at the start of our QRS complex. So this is our P-R segment. And with our second segment, it's our ST segment, which again is going to start at the end of our QRS complex and end right before our T wave starts. And that is our ST segment. Now, what someone might question now is, why do we have all these segments, intervals, and labeled all these waves? Or what do they do and what do they correlate into the heart? So, we will now go into what do these mean? What do the intervals, segments, and waves mean in correlation to our heart? So we'll start here at step 1. Now step 1, we can see our little diagram of the heart here. Now to start our cardiac cycle, we'll first look at this white dot right here. This is our sinoatrial node, or shortened down to our SA node. It's what stimulates our heart to start beating. Now what the sinoatrial node is doing is it starts this depolarization of our atriums. Or more simply put, it causes atrial depolarization. So our depolarization event, we will color in as green. So our depolarization from our SA node will begin and be around here at the top of our heart, right above our 2 atria. Now looking at the start of our EKG form, we can see that our P wave has just started to form. Now our P wave here, or at least the start of it, is depicting our atria depolarization. Now we move on to where our depolarization event leads to. Okay, so now we're going to step 2. So step 2, we will focus on the heart first, so the physiology, and not look at the EKG until after we label and talk about what the heart is doing in this step. So first, we're going to start by diverting our attention from our SA node here to our little node down here, which is our AV node, or called our atrioventricular node. And alongside this AV node, we're also looking at our AV bundle right here, which goes down the middle of our heart, the wall that's separating both our ventricles. Now our AV node, as you can see here, is in our right atrium. Now why do we need a AV node if we already have our SA node here? Well, that will become apparent in just a moment, but what we want to look at first is our depolarization event and where it's conducting to. So at this point of going from step 1 to step 2, our atriums have been depolarized. They are depolarized. But our depolarization event is now conducting to our AV node, which conducts to our AV bundle. So our step 2 is encompassing the conduction to our AV through our AV bundle. So our conduction will be, again, our atria, and it will have conduction through our AV node as well as our AV bundle. But in step 2, it hasn't conducted all the way down to our apex yet. So it has not reached down here yet. Not yet. Now what does this conduction of our depolarization event do to the heart? So the two important things that happen during this step are, one is our atria contract. Again, due to this conduction through our AV node and AV bundle. So our contraction of our atria is going to be a systole moment where it's pushing blood out. So I'll label where the heart now is contracted to in red. So our 2 atrium will squeeze in about, this much and this much, just enough to pump blood where it needs to go. If it's on the right atria, it's pumping it into our right ventricle. Now looking at our left atria, it will be squeezing in to pump blood into our left ventricle. This is the first important thing that happens during step 2. Now the second thing is our AV node delay. So why do we want an AV node delay? Well, having this AV node delay ensures that both our atria have enough time to contract and completely empty their blood into the ventricles before the ventricles here begin to contract. So if we don't have this AV node delay, what might happen is that not all the blood from our atria here will actually go into our ventricles. which will lead to less blood being sent to the lungs or out to the body, which is not good. So step 2 encompasses a lot. It's having the atria contract, the AV node delaying so we have enough time to get all our blood into the ventricles, and it's showing a lot of our blood movement here. It's showing half of our blood movement basically within the heart, from the atria to the ventricles. Now we can turn our attention to our EKG here. So with our EKG, we can see that our P wave here is complete. We can see our P wave here is complete, which I'll label just P. And then we can see right here, the area right after our P wave, which is our PR segment, which should not be confused with our PR interval, which starts at the beginning of our P and ends at the start of our QRS complex. Our PR segment is between the end of our P wave and the start of our Q wave. This is our PR segment. Now this is where you can see the importance of knowing these segments and intervals. This segment, this PR segment being made or being formed is due to all of this. And to be more specific, it's due to our conduction through our AV node into our AV bundle. That is what's creating our PR segment. So our PR segment can tell us a lot about what's happening in the heart. Having a normal PR segment can tell us that we have atria contracting and an AV node delay. That is why we have a PR segment. That's the delay. Without this delay, we wouldn't have a PR segment. But the main thing with this step 2 is just realizing the importance of these segments, and they're not just splitting up our EKG waveforms. We can separate these segments and single them out so we can actually see differences between EKGs and try and make diagnoses or prognoses about what is happening. Now that leads us to our step 3. Now with our step 3 again, which each of these steps we'll start with the heart and what it's doing, the physiology of it, and then move on to our EKG. So looking at our heart diagram again, what should we be looking for? So we're thinking of our conduction here. So now the conduction of our signal is in this middle part right here of the heart. That's a wall separating both our ventricles. Now in this case, in step 3, we can label our entire depolarization conduction right here. But one thing to note, it has not reached the apex yet. It has not reached that yet. It is staying right here in the middle wall of the heart. Now one thing someone might question is, what about in step 2, going back to step 2, where does this atria contraction go? In step 3, we still have this atria contraction. It is still contracted here. There's been no change in its contraction. Not yet, at least. So our atria are still contracted. And this is really all that's happening in step 3. The importance of step 3 is showing that the conduction of the signal is going down the heart still, trying to reach the apex, but it has not reached the apex yet. Now we can move over to our EKG, which, looking at our EKG, I won't label the PR segment or the P wave again, but what we can see is, again, still a complete P wave, our PR segment, and then right here, what we see here is our Q wave, the start of our QRS complex. So what we can say about our Q wave is our Q wave can help us visualize the communication or the conduction communication between our atria and our ventricles, because this step 3 going down the middle of this wall of the heart is a part of our conduction communication pathway here. So a normal Q wave, a normal one, can signify that we have normal conduction down the middle of our heart. Now step 3 was kind of quick because there's not too much to say about it. But now we go on to step 4. So what is happening in step 4? The conduction has gone down this middle highway and it has landed in the apex. Now, that doesn't mean the conduction is gone from the middle area. It is still there. It is very much still there, but it has reached the apex. More specifically, it has reached the apex of the ventricles. Now, this isn't all that's happening here. Now, one thing to remember is that now we have our atria relaxing. So one thing about the QRS complex, during this QRS complex, atria relaxation occurs. Now we didn't see it in step 3 with our Q wave, but during this QRS complex, the entire thing, it's starting to relax the atria. But here in step 4 is where it will become more apparent that our atria relax. So it goes back to normal here. There's no more contraction here, which now we'll label a new thing that's in blue. So during this step 4, the new thing that happens is a repolarization event, and that occurs in the atria. Here's our repolarization, and I'll label it to repolarization. Again, remembering that green is depolarization. What we can kind of write on the side here to put in words is that our atria repolarize. We can also put down that the apex of ventricles depolarizes, and we can put the atria relax. Now, all this happens due to the conduction moving further down the heart. Now, one thing you might notice here is that there's this area here that doesn't have our repolarization event or our depolarization event. Now, going a lot more into action potentials, which I won't do, you can understand exactly how this is all working in regards to action potentials. We're just going to stick to a bigger picture for now. Now let's go back to step 3 real quick. So writing down what's happening here, again, we'll just say our atria are still contracted. And our highway here, or we will call it our midwall, which I'm calling it that because it's in the middle of the heart and it's a wall between the two ventricles, but there are more specific and terminological ways to say it, but we're just going to say our midwall here is depolarized. Still focusing on that it has not reached the apex yet. Now that we've gone through what the heart is doing in step 4, we can move over to our EKG waveform. So again, we can see our P wave, our PR segment, our Q wave, and then we see the first half of our R wave. So again, we have our Q here, and we have our R here, but the R wave isn't finished yet. But this is the R wave coming towards our positive electrode on our heart monitor. So alongside having our Q wave helping determine our communication of conduction between our atria and our ventricles, the entire QRS wave is what we would look at to determine if our communication of conduction is interrupted, blocked, or there at all. So with this R, with seeing this R wave form here, or at least half of it, we can go back over to our heart and see, again, we have our depolarization event at the apex and still at our midwall. Now, if we didn't have any depolarization conduction into our apex or midwall, we wouldn't have this R wave. And that would indicate to us that there's an issue with something above this, or at least something above the apex. So that leads us to our step 5. Now, step 5, let's look at the heart again. Now, the first question that we're just going to go straight off the bat with is, where has our conduction gone to? Where is it conducted? So our conduction has now gone from the apex and is now rising back up. But don't get it too confused. It has gone lower on our midwall here, but it's still at our apex. It's just radiating base. It's just conducting from our apex up our ventricles. Now what this depolarization here is telling us is that we have now depolarized our ventricles. So our ventricles are depolarized in step 5. Depolarized. So our ventricles are depolarized here. And that is the main point of this step 5. Now the repolarization event in our atria is now done. Our atria are back to now resting. There's no more repolarization or depolarization in our atria. And the main point of step 5 is this ventricle depolarization. So now we can move over to our EKG. Now we can kind of see now a more finished EKG. Now the first thing we can see here is that our R wave has been completed, is now its full state, and we see our S wave now. So by step 5, we have our QRS complex finished. QRS complex is now completely formed on our EKG. Now it would be important to look at now what the QRS complex fully encompasses. So we'll go back up here to step 3, which still has our atria contracted and our midwall is depolarized. So what does our Q wave indicate? There's still contraction and our midwall is depolarized, the highway between our atria and our ventricles. Step 4 is showing us that the atria is repolarizing, which, to put lightly, is a side event that we will not focus on here. We are looking solely at our ventricles. So the important thing of our step 4 with the R wave forming is we see the conduction reach the apex of our ventricles, depolarizing the apex. And we can also see that our atria has relaxed. Now with the end of our QRS complex with step 5, we can see our ventricles are now depolarized. Now from steps 3 through 5, we can see the true implications our QRS complex can give to us, which, to put simply, is seeing a large part of our conduction communication between the atria and the ventricles. Now we'll go on to step 6. So here's step 6. Let's look at the heart. One thing that some people might have already kind of figured out, after this depolarization, a contraction is happening. So our ventricles are going to contract. So with that, I will pull out our red again. So our ventricles, which their contraction will be shown in red, are contracting. Now they're contracting, but we do see these 2 valves open, which is not a correct thing. So what these valves are in the heart, which each has a specific name, now just know the basics between these 2 kind of gateway pumps between the ventricle and the atria is that they are a one-way valve. They are valves. Now to explain how these valves are one-way, now when there's high pressure in our atria here, it can push through this because the doors or the valves are bent into the ventricle. Now when there's high pressure here in our ventricle, why can't it just go back into the atria? Well, it's because, again, like I said before, this is a one-way valve. And it's one-way valve because if you try to go back into it, it's closing due to its conformation and how it's shaped. You can think of it like a Chinese finger trap, kind of. So your finger can go into the Chinese finger trap fairly easily, or at least your finger can go into the Chinese finger trap without too much struggle. Now, trying to pull it out, and in this case, pulling your finger out of a Chinese finger trap is going from the ventricle to the atria, is very difficult. And in this case, you can't do it unless there's some sort of damage to our valves. It's just a one-way road here. from atria to ventricle on both the right and the left sides. Now I'll just write out kind of what's happening here. So again, very important just to remember this. Step 6, our ventricles contract. And that is a systole movement, or a systole action, which means it's contracting and pushing blood out of the ventricle. Now a diastole movement is widening and letting in blood. So when we said that our atria was relaxing, it was going from a systole to a diastole moment there. Because it's going from pushing blood out to opening so blood can rush in. And then the extra thing I'll just put down right below this ventricles contract note is that our valves are one way. Now, one thing that I probably should have said at the very beginning, but the ventricles contracting was a very important notion, and it was based off of our depolarization event, because after something depolarizes, a contraction is usually going to happen. So where is our conduction leading to now in step 6? Now it's actually going still up our heart. So it's still here in our midwall and the apex, but it's reached higher here. So if we try to look at our step 5 and our step 6, we can see our step 5 or our step 6 is much higher up these ventricles. It's not as low here. This is because our ventricles, yes, they're depolarized in step 5, but in step 6, our depolarization event is conducting through the ventricles, and that is what's causing our ventricles to contract. So now we can move our attention again back over to our EKG here. And going through all over it again, we see our P wave, our PR segment, a Q wave, our R wave, our S wave, and now this right here. This block, or this line here, is our ST segment. So going back into yellow, if we remember correctly, our ST segment starts at the end of our S wave and begins right before our T wave. So our ST segment is between the end of our S wave and the beginning of our T wave, before the T wave even begins. Now, why might looking at our ST segment be important? Well, it can seem very important just by the fact that our ventricles are contracting here. So when our ST segment is normal, our ventricles are contracting like normal. If our ST segment was elongated, that would mean that our ventricle contractions won't be in sync with our atrial or atria contractions. Now, our ST segment would be important because our ventricles contract here during this segment. So our ST segment can give us more insights into our ventricles contraction and seeing if there's any issues from our apex up our ventricles with its conduction communication. Step 7. So again, we're going back to the heart. So what's now happening? We've had our ventricles contract, the depolarization is conducted up the ventricles, basically encompassing the entire ventricles, and it does eventually between 6 and 7 encompass the ventricles. So what happens next? So what happens now is that we have a repolarization event. So first, I'm going to color in where our depolarization event is at now. So our depolarization event has considerably gone farther down the ventricles now. It has become less apparent in our ventricles. Now it's still up the same amount in the midwall here, but in the entirety of the ventricles, it has lessened. The big thing that's happening in this step 7 is our ventricles are repolarizing, which I'll put here. So where does that show up on our heart diagram here? Well, it shows up from basically this top of our ventricles here, down this wall, around the apex, back up to around the same spot right here. So our repolarization event is right under our depolarization conduction. So what this is showing us is that our heart, or more specifically our ventricles right now, are coming back down to its resting membrane potential. So this depolarization green is now decreasing in charge. It's going more negative, closer back to its resting. And that's the main part of step 7. So we can go over to our EKG now and kind of analyze what's happening here. So again, repetition is key with knowing these waveforms. We start with our P wave, our PR segment here, which then goes into our QRS complex, then into our ST segment, and now in step 7 we can see the upward deflection of our T wave. This is our T wave, or at least the upward deflection of it. And this, again, is our ST segment, just for repetition's sake. Now, why might our T wave's upward deflection be important to us? So, our ventricles repolarizing is what's depicted by our T wave here, or at least the upward deflection of it. So, seeing a T wave normal is telling us that our repolarization is going as normal. And without a normal repolarization, there can be many things that happen. If we can't get back to a certain resting potential, that can lead to both sides of extreme spectrums of what the heart will do. Now with our upward deflection of our T wave here, the reason why it's important is not just because our ventricles are repolarizing. It can indicate to us, at least a full T wave will indicate to us, a recycle of our cardiac cycle. So without a T wave, we're not going to see the repolarization of our ventricles here, which then will lead to the heart going back to its resting membrane potential. And without going back to the resting membrane potential, a lot of issues can arise. So with just our upward deflection, we can see our ventricles repolarizing. And we can see with this example how the EKG is different than an action potential. Because with certain deflections upward, it might match with a depolarizing event, such as an action potential being a depolarizing event when it's an upward deflection. But here, we have our upward deflection of our T wave, and it's a repolarizing event. That is why you have to be careful with not mixing up EKGs and action potential waveforms. And then the last thing to note that I missed here is that our ventricles are still contracting, or they're still contracted here. So there's been no loss of contraction yet. So our ventricles, which I'll put here, are still contracted. Now we can move on to our final step here, which our final step is step 8. So we have our step 8 here. Now what's happening in step 8 and what is the heart doing? Now to start, our ventricles are now relaxed. So they are not contracted anymore. They are relaxed here. Now what else is happening in this final step? Well, there's no more repolarization or depolarization here. Both those conduction signals are now absent in this final step. Now what the heart is doing now is preparing for the next cardiac cycle. And it does this by returning back to its resting membrane potential. This means there are no repolarization or depolarization events occurring at this moment, and it is simply going back to its neutral state of rest regarding its membrane potential. Now this is the heart getting ready for the next cardiac cycle. From step 8, it will go back to step 1 of atria depolarizing because a stimulus has hit our SA node, which then it will go back through steps 2 through 8 and back up to 1 again. And now finally, with this final step, we'll look at our EKG, which again, for repetition's sake, P wave, PR segment, our Q wave, RS complex finished, and this is our ST segment, our T wave, done. That is our EKG waveform, or at least it's a snippet of it. It's one cardiac cycle. Now, to go a little bit more into this, again, remember this is our T wave, and what does it mean here? What does it finishing mean for us? So with our T wave being complete and not being erratic in some way in its second half, or the T wave just even being present, it's showing that our ventricles are relaxing and our heart has returned to a resting membrane potential. Without our T wave being present, that is going to indicate to us that there might be an absence of relaxation of the ventricles or an absence of the heart returning back to its resting membrane potential. Now, both of these would be bad because they would delay the next cardiac cycle. So that will impact the heart in some way. Now, from this step 8, again, it's called the cardiac cycle or the electrical events of the cardiac cycle. From this step 8, it'd go back to step 1 where we have a stimulus stimulating our SA node, which then will depolarize our atria, leading to step 2, back through to 8, and then again going back in the cycle of 1 through 8, 1 through 8, 1 through 8, and that is the cardiac cycle with its electrical events. So with this understanding of an EKG, we can now look at a normal EKG to find different degrees of blocks and types of fibrillation, and also an elevation. But first, we'll look at some important questions to ask when looking at an EKG. So what to ask when reading an EKG? First question we'll go over is, what is the rate? Is it normal? So a normal rate is usually 60 to 100 beats per minute. And when we're looking at this 10-second interval here, if we count them, it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That'll just be 11. So every 10 seconds, there's 11 beats. And in 1 minute, that's 60 seconds. So times that by 6, and it equals 66 beats per minute. And that's in our normal rate range, which is between 60 and 100. Now for some people like long distance runners, it might be different, but for the normal person, and the normal rate for that normal person will be between the 60 to 100 beats per minute range. Okay, so the next question is the rhythm normal? And what we mean by normal here is the rhythm missing anything, or is it off by anything? So we have to make sure there's no missing beats. So if there's a dropped beat, there'd just be a straight white line here. That would not be a normal rhythm. And another indicator of not a normal rhythm, there's any of these segments or intervals are larger than the rest of these. So if there's inconsistency, that's messing up the rhythm. That is the majority of what makes up a rhythm. And to know if a rhythm is normal, everything is consistent and into the standards of what a heart rate is for the normal person. Again, there can be some differences depending on the person. The third question is, are normal waves recognizable in form? So this plays in with the second question, which is the rhythm regular or normal. Now we're looking at, are the waves that are there, the normal waves that are there, recognizable? So there can be waves that can be here, and they can be our R here, our T wave here, and if any of these are irregular in some way, where they're either not recognizable because they are in a weird format like that, or maybe they're really small, or maybe there's just some deformity or difference in them that makes them unrecognizable, then that would be a concern. Which you would be able to see some of these questions in play in later examples of blockages. But with normal waves being recognizable in form, it's just being able to actually pinpoint which wave is which. Because to a certain point, they become unrecognizable, especially when we go into fibrillations. They're not going to be able to be recognizable. So the next question is question 4, which plays into question 5. So I'd say question 4 and 5 are one question, but depending on how you answer, it leads to question 4 or question 5. So the first thing here is there one QRS complex for each P wave? So is there one of these are Q, R, and S wave complex here for each one of these P waves? And here, this is a normal EKG, so there is one P wave for each QRS. So that's normal. Now, if yes, so if there is one QRS complex for each P wave, we'll look at if the PR segment is constant in length. So this little area in between our P wave and our QRS complex, or our Q wave to be more specific. And if these lengths are all constant along our EKG, that's normal. And later when we look at the other blockages, we can see the difference fairly easily. And now into question 5, where question 5 is if you said no, there isn't one QRS complex for each P wave. So what happens here is we're going to want to investigate a bit more by finding two different types of heart rate, using the first one with our P waves and the second one with our R waves. Our P wave rate is called our atrial rate, and our R waves are our ventricular rate, or what we're usually referring to when we are saying what's the heart rate. To actually calculate P wave rate, we would use the equation, and I'll short it down to AR for our atrial rate. It would equal 60 divided by the P wave interval, and that's in seconds. So let's just say this EKG here. As we can see here, these are very short P to P wave intervals. Now if we just kind of ignore this P to P wave interval and we just go solely based off of waves, the amount in these 3 seconds, we can count 1, 2, 3, 4, 5, 6, 7, 8. There's 8 P waves in these 3 seconds. And we're going to modify this equation real quick. So first what we're going to do is take how many seconds we have and divide it by 60. So this would just be 20. And our equation will change into our number of P waves, 8, times 20, which gives us 120 per minute. Now the reason why we're getting two rates is because we want to compare them just for helping with the thought process. So 120 beats per minute for our atrial rate. Now we go to our R, or our ventricular rate, which is what we're usually referring to when we say heart rate. So again, this is going to be around 3 seconds. G. 3 seconds. And let's count the R waves. 1, 3 in 3 seconds. Another thing to mention here is that we can see this weird dip here where our S wave is supposed to be, or our normal S wave is supposed to be. Now this is a very good indicator of a 3rd degree block, which I'll go into later. So if we have 3 R waves, just do 3 times 20, 60 per minute, which is actually in our normal range from 60 to 100. Now one thing to mention here, we can see we have a big difference between our atrial and our ventricular rate. But why are they different? Well, first, are they the same? That's a big no. See a big difference. It's between 60 beats per minute for our ventricular and 120 beats per minute for our atrial. Very big difference. So now the question comes up, since we have two different rates, what is the one that we usually measure? And that is our ventricular rate. And that's because the ventricular rate is measuring the blood going out to your body. Now you're actually pumping it between chambers. That's what the atrial rate is doing. It's measuring the blood going through the chambers of the heart, not actually going out to the body. So when it asks which rate felt at the wrist, that would be our ventricular rate, which for our example was 60 beats per minute. So now let's first look at a normal EKG. So what we see, let me grab my laser pointer. So what we can see first is that all of these waves happen in irregularly spaced intervals, or they're in unison. They're very uniform. And there is a regular rhythm, which encompasses a lot. Regular rhythm is a very general term that encompasses a lot of normal things. But first, we can see our QRS complexes equal the amount of P waves. So we have QRS complex and we have a P wave. That is equal here. They are equal. And alongside this QRS equaling the amount of P waves, we see constant length in our PR segments. The segments right here, they're very constant in their lengths. There's no variation, or at least no noticeable variation. And the two final things to kind of see from this small little snippet is that there's no drop in beats here. There's no drop of a QRS complex or an entire beat whatsoever, and we have a normal heart rate range, which is, in this small snippet, it's 66 beats per minute. If you counted all these, which there's 11, and then you take 11 times 6, and you get 66. And our normal range for a heart rate is 60 to 100 beats per minute. Now we'll look at 3 degrees of electrical blocks, and after those 3, we go into fibrillations. But first, what do we mean by a block? So what we mean by a block is an electrical block, which is a conducting circuit being affected. So it's not an actual physical block, like if you have a coronary artery being blocked by some foreign object or by some fatty deposits. It is some affected area in our conducting circuit. So there is somewhere in our circuits in our heart that is affecting, delaying, or completely stopping our depolarizing wave from going through it. Now first we'll look at a first degree block. So right here, for our first degree block, we have our normal EKG right here, and here's our first degree block EKG. So the first things we can see here with our first degree block is that there's a normal rhythm. There's uniform patterns here. And we can also see our QRS complex number is equal to our P wave number here. So we can see P wave, QRS complex, P wave, Q, P wave, Q, P wave, Q. Now, what is the issue here? Or what is the abnormal part of our first degree block? It is our long PR interval. So if I grab my pink right here and we look here, here's our PR interval for our first degree block, and here's our PR interval for our normal EKG. It's almost double in length. That is the abnormality that points to a first degree block. Now, what this long PR interval indicates to us is a delay in conduction from the atria to the ventricles. So if we made a little heart diagram here as a box, here's our atrium, 2 atrials, and here's our 2 ventricles. It is blocking somewhere the communication conduction between the two. So down the mid-wall, there's something delaying it. And that is all that encompasses a first degree block. And that can lead us now to our second degree blocks. With our second degree blocks, there are two types. Type 1, or Mobitz type 1, we're just going to shorten to M1. And then we have a second type called Mobitz type 2. And we're just call that an M2 second degree block. Now, looking at this, we can see the first thing most people would notice is this very empty space right here. This is a drop in a QRS complex. Now you might be wondering, well, isn't this blocking an entire beat? No, because we have a P wave right here, and we have a P wave right here. So we're missing our QRS complex, which makes it so we can't have a T wave. So to have a T wave, you need to have a QRS complex. Now we can see a similarity between this Mobitz type 1 second degree and our first degree block, and that is the prolongation of our PR intervals. But there's a difference. Now the difference is that as we go along with each occurring beat, our PR interval is getting larger, and it keeps getting larger until we have a drop in a QRS complex. And what this usually indicates to us is a block in the AV node, which, if we remember what our AV node does, our AV node is making that delay between our ventricles and our atria just so we can have a rhythmic beat and make stuff timed correctly. Because without timing with our delay from our AV node, things can go awry. Now we can go to our second degree M2 type. Now the first thing people will notice again is this drop of a QRS complex. So that's what makes both of these Mobitz types type 2, is this QRS complex drop. Now what's the difference here between Mobitz type 2 and Mobitz type 1? Well, the PR intervals here stay constant. So there's no prolongation, elongation, whatever you want to call it, of our PR intervals. They stay constant like our normal ones do, and they're not long. Now then you might be wondering, why does our QRS complex drop here then for our Mobitz type 2? And that is usually due to our P waves not conducting. So there's some issue with our P waves not being able to conduct and cause our QRS complex to form. Now we're on to our third degree block, which we've seen before. So with our third degree block, we can see quite a few differences. So the first thing you want to notice is that there's no T waves here. All these bumps here that we can count here are all P waves. There are no T waves to be seen. And then we can see that this S part of our QRS complex is deformed in some way. It's going a lot farther down. So going back to our P wave count, this makes it so the amount of P waves we have exceeds the amount of QRS complexes we have, as well as our QRS complex with our S wave in particular being abnormal. Now, what does a third degree block indicate to us? So it's telling us a few things. So first, it's telling us that there's a complete blockage of electrical signals between the atria and the ventricles, causing the two to be independently of each other. So there is no relation between the beating of our atria and our ventricles with a third degree block. And to put more into EKG terms, there's no relation between our P wave and the QRS complex anymore. Because we can see P wave here, no QRS complex. P wave here, then we have one. And then P wave here, none. There's no relation between them. There's no pattern. There's no unison. There's nothing connecting them. And that is, again, due to there being a complete blockage between the two, causing them to independently beat between each other. Now we can go on to our next type of issue, which is fibrillations. Now, the first thing the question is, what is a fibrillation? A fibrillation refers to the rapid and uncoordinated contraction of muscle fibers, and in our case, cardiac muscle fibers. And we're going to be covering two types of fibrillation, and we'll start with our atrial fibrillation, or shortened down to AFib. So with atrial fibrillation, we can see here that we can see a very pronounced R wave here. And we can notice that it is an R wave. But when we look between them, we just see squiggle lines that are not showing any pattern or uniform to them. This would indicate to us that there's no recognizable P waves, and alongside that we have an abnormal QRS complex. Because here we can see, oh, there's no Q wave here, or here we can see both and then our R wave, but over here there's just going to be random abnormalities with them. And what this non-recognizable P wave and abnormal or irregular QRS complexes tell us is that there is a rapid and chaotic heartbeat. Now to just get into like an extra little tidbit of information, these squiggle lines or these weird waves in between all these QRS complexes are called our F waves, which is just an extra thing to know. All these little squiggle waves between our QRS complexes are called our F waves. Now we'll go on to our ventricular fibrillation, or shortened down to VFib. So here, there's nothing really to point out here in its EKG because it is all just messed up. So what this very chaotic drawing here is showing us, or our chaotic EKG is showing us, is that our ventricles are not functioning. There's an absence of normal waves, a chaotic rhythm, and alongside seeing a ventricular fibrillation, you will feel no pulse on the individual. But the EKG will show this high rate. But again, there will be no pulse to be felt. Now, this VFib is not a heart attack, but it can lead to one. And to go back and just say a quick thing about our atrial fibrillation is that it's not that dangerous unless it occurs for long periods of time and it's prolonged, but it is not an indicator for anything major to happen that instant. And now we can go on to our last thing of this video, which is our ST elevation myocardial infraction, or shortened down to a STEMI. Now looking between our STEMI right here and our normal, we can see a few things. One, we can see our P wave here, and we can see the start of our QRS complex. But it ends early and makes this ST segment here is a lot higher than it should be. So right here from our S to the start of our T wave right here, the small elevation, this is our ST segment and it's very elevated. To get more into specifics, a STEMI is a type of heart attack which is characterized by, well, what the name suggests, an elevated ST segment. This could show up due to damage in the heart or due to a complete coronary artery blockage, which is not referring to a circuit blockage. This is a blockage of a heart vessel or an artery, the coronary artery to be more specific. So there's some physical blockage here or damage that is causing this type of heart attack. It is not a conducting circuit blockage. And I hope this helped. This was everything to do with electrocardiograms, and I'll see you in a later video. Hey, I gathered some extra resources and videos I found helpful, all linked in the description. I'm also on Twitch. Come stop by sometime. And if you have any topic you want to see me stream or make a video for, feel free to comment it. Thanks.